Hello, and welcome to your fourth neural network lecture. So I think it's appropriate that we end our neural network lecture series by talking about the biggest problem in data science, which is the bias-variance trade-off. In our previous course, we talked a little bit about the bias-variance trade-off and what it meant for training machine learning models. When we look at this chart, we can see that as we increase model complexity, we go from an area of high bias, where our model is too simple to approximate the relationship between our inputs and our outputs, and an area on the right-hand side that has high variance, where our data is too complex and it overfits to the data that we have, meaning that it performs very differently on data it's seen versus data it hasn't seen. Basically, the bias-variance trade-off says that if we're in this area of really high variance, we can actually move over by increasing our bias and therefore decreasing our variance. Hopefully this will get us in this sort of Goldilocks zone where both our seen data, the training data, and our unseen data, the testing data, are both performing well. In previous lectures, we talked about the fact that neural networks are really powerful because they allow us to approximate really complicated relationships between the inputs of our model and the outputs of our model. When we stack a bunch of different layers together, we can get some really complicated relationships between inputs and outputs. However, with great model complexity comes a huge need for regularization. Regularization are practices that help us move from that area of high variance, hopefully closer to a middle zone where we're not overfitting our model to data it's seen before. So today we're going to talk about a couple of different ways that we can regularize neural network models. Let's start with a way that you should be very familiar with from the previous course, which is penalization. Penalization typically works best for smaller networks. However, it works pretty much the same as like a lasso or a ridge penalty that we learned about that we can apply to things like linear regression. Neural networks, just like a linear regression or a logistic regression, have a bunch of different weights in the model. And all of these weights can be penalized. The penalty basically serves to make sure that the weights are not too big. In the same way as a lasso or a ridge regression, penalization works by taking our typical loss function, whatever it is that we chose, and adding some penalty term multiplied by a regularization strength term, which basically determines how big of a penalty we're putting on the weights. And this penalty term here, represented by this omega function, can pretty much be anything, but common versions would be an L1 or an L2 regularization. Just FYI, we typically only penalize the weights of the model, not the biases. This is because biases tend to be more easily estimated, and when we regularize them, it can actually lead to our model underfitting. This type of regularization basically works by saying if a certain parameter does not actually improve our loss that much, then we can make it a lot smaller or regularize it by applying that penalty. This point here basically represents what our weights would be if there were no penalization. As you can see, when we move in this horizontal direction, changing our weight 1, doesn't actually have that big of an effect on the loss of our function, at least compared to the other variable. Because it doesn't have as large of an effect, our regularization actually drags that weight from, let's say right here, all the way over here. However, if we look in the vertical direction, when we change our weight, the loss is actually increased quite a bit very quickly. This means that weight 2 has a huge effect on our loss. And you can see that the regularization that happens, taking our weight 2 from about here to about here, is much smaller. Now, I won't make you work through all the math, but if we apply L2 regularization to our weights, which is similar to a ridge regression, we end up with a new update rule when applying something like gradient descent. We know that our typical update rule is that our new weights are our old weights minus some learning rate times our gradient. We can see that the new update rule that's derived from applying an L2 penalization on our weights basically changes our update rule. We're still applying the same change, the learning rate times our gradient, But before we do that, we actually take our previous weights and shrink them down a little bit. Therefore, you can see that at each step, we're actually shrinking all of our weights a little bit before applying our update. And L2 regularization is not the only way we can penalize our weights. We can also use an L1 penalty, which is similar to lasso. Just like with lasso, an L1 penalty still penalizes large coefficients for being big if they don't improve our loss function. But unlike L2 penalization, L1 penalization encourages sparsity, meaning that it'll drag some of our weights to exactly zero, thus basically removing them. So in summary, just like we applied penalties with lasso and ridge regression, we can also apply penalties like an L1 or an L2 penalty to the weights in our neural networks. This basically penalizes large weights that don't improve the loss of our model, thus regularizing and simplifying our model. Another way that we can regularize our models is with something called bagging. Bagging should be familiar from back when we learned random forest in our previous course. Bagging, which is short for bootstrap aggregating, is essentially when we take a bunch of different models, train them on different subsets of data, and then average them in the end. Bootstrapping is where we take our original sample of data and basically resample it by randomly selecting different rows from that original data with replacement. This means that we end up with a new sample of data where some rows might appear multiple times and other rows might not appear at all. This again has the effect of having every single model seeing different samples of data. Bootstrapping basically ensures that the different models see different inputs and therefore have different structures. And we can apply this idea to neural networks. We could use bagging to get different subsamples of data to train different neural networks on, and then in the end, average them all together. But it turns out we may not actually need to do that. Neural networks are very sensitive to random initializations, like where we start our weights off at, or things like which data points are in which batch as we're updating our parameters at each step. So it turns out that randomizing those things will still give us slightly different neural network structures that we can then combine or average together in the end. However, one big downside of this is that it's very computationally expensive. Depending on how big your neural network is, it might be prohibitive to try and train a bunch of different neural networks just to then average them together in the end. All right. Let's talk about a similar related way of regularizing our neural networks called dropout. Dropout actually operates on a very similar idea to random forests, which have bagging and random feature selection. The idea in a random forest is that while individual trees might overfit to the data that they see, not every tree sees the same data. So while individual trees can overfit as an ensemble, the model can't overfit because different trees are seeing different information. So they can't all overfit to the same patterns of noise in the data. Dropout operates on a very similar principle. During training, Dropout will randomly select nodes in each of your layers and just completely zero them out or remove them. This means that during training, we never know which nodes are not going to be there, which means that our network can't over-rely on the connection between certain nodes. Let's look at an example of what this might look like. Here we have a small but fully connected neural network. Typically, when we train this neural network, we'll do a forward pass, which will send all of our inputs through the network and get a prediction, and then we'll do a backwards pass where we do back propagation in order to update the weights in our model. The idea behind dropout is that when we're training, every time we update, we will drop random nodes from each layer in our model, just completely removing them from the model. This means that when we do our forward and our backwards pass, some of those nodes just aren't there and they're not a part of training. The next time we want to make an update, we may drop different nodes like these instead of the ones that we dropped before. Again, we'll continue on with our training process, but this time with these nodes removed. So as we train our model, it can't over-rely on certain connections between nodes because during some points in training, those nodes were just completely removed from the model. Mathematically, the way we do this is by taking an output from a layer and then randomly deciding which of our nodes we're going to set to 0. In this case, I wanted about 20% of my nodes to be set to 0, and randomly it chose to drop this one. So we took the previous values and left all of them the same except this one, which we then set to 0. thus basically dropping it out of the network. Now, just a quick mathematical note. When we zero out some or many of the outputs from a layer, that means the values in the next layer on average are going to be closer to 0 because we just set a bunch of the values coming into that layer to be 0. In order to combat this, what we do is we take the remaining non-zero values and we scale them by 1 over 1 minus the probability of a node being dropped out. In this case, my dropout rate was 0.2 or 20%, and so I scaled all of these up by 1 over 0.8. This ensures that the expected values that are feeding into that layer remain around the same, even though we're setting some of them to 0. And while sometimes we might want to have the same dropout rate for every single layer, for instance here for each of the different layers we drop out about on average 20% of our nodes, we actually can set these to completely different values. So for instance, because these two layers are very densely connected, we might want to set the dropout rate here to be about 0.5 so that it's losing more of its connections every time we're training. Every iteration that we're doing when we're training, we're going to randomly drop out different nodes, but this dropout only happens during training. Once our model is fully trained using dropout, when we're doing a prediction from our model, we actually don't use dropout because we want to use now the fully trained network. So again, dropout of random nodes only happens during training, not when we're actually making predictions from our model. Just like a random forest was an ensemble of decision trees with slightly different structures, you can think of dropout as basically approximating an ensemble of different subnetworks, all of the different possible networks we can get by dropping out some of the nodes. Dropout is really cool for a few reasons. One, as we're focusing on this lecture, it helps regularize our model, taking it from overfit to hopefully in that middle ground where we're doing well on both our seen data and our unseen data. It's also pretty computationally inexpensive, and because of how simple it is, all we're doing is zeroing out different outputs from different layers, it's really easy to implement with all different sorts of structures of neural network. All right. On to early stopping. Early stopping is another way to regularize our network, and actually I can explain it with just this picture. Often when we're training our models, what we'll see is that both the training and the validation error at the beginning start to both descend. And then as we get to a certain point, our training error keeps going down, but our validation error actually sort of plateaus and then starts rising again. Once it starts rising and there's a difference between the training performance and the validation performance, this is when overfitting is happening. So wouldn't it be nice if in the training process we could just keep going until we start to see our validation error rise and then just stop? Yes, it would be, and that's exactly what early stopping does. Early stopping basically says that as we're training our model, we can watch our validation error, and if it stops improving or if it even gets worse, then we should probably stop training our model because it's on its way to overfitting. And it's pretty much as simple as it sounds. We watch our training and our validation error through this entire process. And if we see that the validation error isn't improving, then we stop and we return whatever parameters of our model got us to this place. Now, typically we want to give our network a little wiggle room, and so we have a variable called the patience for early stopping, which basically means that we set a certain number of iterations where our validation error can remain the same or maybe even get worse, and we'll still continue to train the model just to see if maybe the validation error will get a little bit better in a few iterations. In other words, we can basically set something like 5 iterations and say, look, if I see my validation error plateauing or getting worse, I'm going to give you 5 more iterations to see if it keeps improving, and if it doesn't, I'm just going to stop there. And that's pretty much all early stopping is. We're monitoring the training process using a validation set in order to see if we can detect when overfitting starts happening and stop our training at that point. All right, last but not least, let's talk about batch normalization. Now, if you've heard of batch normalization before, you may have not heard about it in the context of regularization, but actually it turns out that it does regularize our models. In our previous course, we talked a little bit about the the importance of scaling our data or normalizing it before putting it into our model. For instance, we could Z-score our data before putting it into the model. Batch normalization essentially works very similarly, but instead of just normalizing data before we put it in the model, we actually normalize the output of all or some of the layers inside of our neural network. So when we have the output of a layer, we then normalize it before sending it off to the next layer. Now, there's not yet been any consensus about exactly why batch normalization works, but we know that it has a couple of really cool effects. One of those effects is it sort of smooths out the optimization that we're doing. For instance, here you can see the contour plot of a loss function, and it's really asymmetric, right? It moves a lot in this direction and not so much in this direction. This can make training a little slower because our updates might sort of zigzag across our space. With batch normalization, it tends to smooth out that surface to make it look a little more like this. In this case, no matter where we start, we have a very smooth and clear path to quickly get to the minimum of our function, thus speeding up our training. So again, batch normalization allows us to speed up our training by having a smoother surface that we are optimizing on, and thus allowing us to maybe increase the learning rate that we use in order to optimize. It also lessens the impact of the initial weights. We talked very briefly about when we start training a neural network, we first randomly initialize all of the different weights of our network, and then we use something like gradient descent in order to adjust those weights to get better and better and optimize our loss function. Where we initialize those weights can have a huge impact on the solution that our model ends up on. However, with batch normalization, it reduces the impact of what those initial weights are because in between our layers, we're just still normalizing our output before feeding it into the next layer. And this also has the impact of regularizing your model. And when we talk about the math in a second, you'll see why. So as we're training our network, we know that typically we're not using all of our data in order to estimate the gradient. Rather, we usually use mini batches, subsets of data that we use to estimate our gradients at every step. Batch normalization takes the outputs of a layer and normalizes them using the mean and the variance estimated from the current batch of data points that we're using to update our gradient. In other words, we calculate the mean of our batch and the standard deviation or the variance of our batch, and then we take all of our outputs and we just normalize it by subtracting that estimated mean and dividing by the standard deviation. This little epsilon here is just a very tiny number to make sure that we're not dividing by 0. Now that our outputs are normalized, they have a mean of 0 and a standard deviation of 1. However, sometimes we don't want a mean of 0 and a standard deviation of 1. So after we've normalized all of the inputs of our layer, we multiply them by a scaling factor gamma and then add a centering factor beta. These are just trainable parameters of your network that essentially rescale and recenter the new normalized data. This allows for the output to have a mean other than 0 and a standard deviation other than 1. Now, because these estimates of the mean and variance are just estimated using a small sample of data, this actually adds noise to the process of training our model, and that noise may be why it has a regularizing effect on our neural network. All right, so today we talked about why it's important to regularize our often very complex neural networks. We also talked about different methods we can use to regularize our model. First, we talked about something very familiar, penalization, which adds a term to our loss function that penalizes the sizes of our different weights in our model. For instance, we could have L1 regularization or L2 regularization, which are like lasso and ridge regression that we covered in our previous course. Then we talked about the concept of bagging. Bagging is when we take different subsamples of our data set and train different models on those different subsamples. Then, once those models are all trained, we use them together by averaging their output in order to make a prediction. While computationally expensive, we talked about how it's possible to do this with neural networks, or just to train neural networks with different initial weights or other randomized processes so that we get a bunch of different neural networks that have slightly different structures that we can then average together. This helps regularize our model because not every one of our models is seeing the exact same data, meaning that it can't overfit to a certain pattern in the data. This is very similar to the idea behind dropout, which is a very common way of regularizing our neural networks. During training, Dropout selects random nodes to just completely remove from the model by multiplying them by 0. We do this over and over during the training process so that while our model is training, it only ever sees some of the different nodes. This results on a network that can't over-rely on certain patterns or connections in our network, because while it's training, we never know when those nodes are suddenly not going to be there. Next, we talked about early stopping, which is monitoring the training process to see when our validation error starts to plateau or even get worse. At that point, it seems like our model is going to start overfitting, and so we want to stop our training process there so that hopefully we can prevent that overfitting, thus regularizing our model. And last, we talked about batch normalization. Batch normalization takes the output of a layer and centers it using the estimated mean and standard deviation from the current batch of data we're training on, in order to have that output have a mean of 0 and a standard deviation of 1. These normalized values are then multiplied by a scaling value and added to a constant so that our output can have a different mean than 0 and a different standard deviation from 1. While we don't totally know why batch normalization works, we do know that it has a regularizing effect on our model, and it also can speed up the training of our model by sort of smoothing out our gradient and allowing us to take bigger steps. No matter which techniques you use, regularization is a very important part of building neural networks, which often can be very complicated and prone to overfitting. Often it's said that the best way to build a neural network is to build one so complicated that it starts to overfit, and then use regularization to reduce that overfitting. All right, that's all I have for you. I will see you next time.